let's talk about inferences for the difference between two means. This is a very common situation in all sorts of research. So when do we do this? Often we do not have enough information to hypothesize a value about the population mean. So in a test of one sample for the mean, we need to have some kind of a benchmark value against which to test, perhaps from theory or something like that. A lot of times we're not doing that. What we're doing instead is comparing the means for two sets of data. For example, if we're a medical researcher, we might want to compare the mean tumor shrinkage or some other metric for two sets of patients receiving two different drugs or two different treatments, or the status quo versus a new treatment, something like that. Or if you could use it for comparing marketing campaigns, you could use it for comparing test scores for schools using two different sets of teaching techniques. There's all sorts of things that you can use this for. We're specifically talking here about independent samples. So when we're talking about the difference between two means independent samples, what we mean is that, for example, if we had two sets of patients and we were measuring their tumor shrinkage, if patient A is over in the first sample and patient B is over in the second sample, there's not any relationship between those two. Okay, so there's a different technique that's related, which is for the difference between two means for dependent samples. And so that would mean if you had basically paired samples, so everyone in the first sample was related in some specific form to everyone in the second sample. Perhaps you were looking at the mean income of husbands and wives, for example. And so you would put the husbands in one group and the wives in one group, and you would compare their incomes or some other metric. And so each one in the first group would get paired with someone in the second group. Or you can do matching and match them up on certain characteristics, even if they didn't come matched together like husbands and wives. So there's different ways to do that. They call that the hypothesis test for the difference between two means with dependent or paired samples. And so that's a different topic. But here we're talking about independent samples. Okay, so let's talk about this approach. So, as I just mentioned, each sample is from a different population, and they are independent. They don't have a connection with each other. So then we are going to talk about if the two means are the same. Okay, so we're going to be setting up null and alternative hypotheses. And so generally what we're going to be looking at is the population. The first sample is drawn from one population, the second sample comes from a second population. We're trying to see if those two populations are equal. So we could actually rephrase this as being very similar to one mean against a benchmark if we look at the differences between the two and consider the benchmark to be 0. So in other words, if the two population means were equal, then we're basically comparing to 0 as the difference. Okay, so there's another way of writing these two hypotheses, which is mu1 minus mu2 equals 0, or else mu1 minus mu2 is not 0, simply by subtracting mu2 from both sides. And so what we end up with that is on the left side we have a difference, and so it turns out that on that left side x bar 1 minus x bar 2 is going to be important. And so we're going to be looking at the sampling distributions of the difference between the sample means, which comes from that left side of this version of our hypothesis test. So in this video, I'm going to be assuming that we do not know anything about the population standard deviations for either population. And so we have a formula for the standard error, and that results in a t-value that we call the Welch's approximate t. There are other versions of this if we know or can assume a value for the population standard deviation. There's another version of it if we don't know the value, but we know that the standard deviations for the two populations are similar or equal. And so if both of those populations have equal standard deviation and variance, in other words, Remember, the variance is just the square of the standard deviation. So we often talk about equal variances. So if we can assume equal variances between the two groups or equal standard deviations between the two groups, then you can use a different formula. We're not going to go into that here. We're going to not make any assumptions at all about the standard deviations of the populations. We're going to base everything on the sample standard deviations. Remember, our test statistic is always subtract what you're comparing and divide by the standard error. So that means that this denominator here is representing our standard error. It's actually an approximation for the standard error. And so this is this denominator here, this square root of s1 squared over n1 plus s2 squared over n2. That is an approximation for the standard deviation of all the set of possible differences between the two sample means, which is a mouthful, but basically it's our standard error, and that's how we're going to use it. Let's keep going. And actually in the numerator here, when we look at the subtract what we're comparing, divide by the standard error, so we're x bar 1 minus x bar 2, that's the difference between our sample means, and the mu1 minus mu2 comes from this part above, and so we're actually going to be comparing that to 0. Okay, let's keep going. As long as both the populations are normally distributed, or as long as both the sample sizes are sufficiently large. Once again, for sufficiently large, we're going to use the rule of thumb of being at least 30. And so this Welch's t is approximately equal to the student's t, which we used before when we did the hypothesis test for one population mean. In this case, the degrees of freedom are going to correspond to the smaller of the two sample sizes. Okay, so to use our procedure, here's what we need to go through. We need to make sure that both the populations follow the normal distribution, at least approximately, or that both of the sample sizes are at least 30. So you don't want to have one, if you have one sample of at least, say 40, and the other sample is only 10, then you don't meet the at least 30 for both. And so in that case, you would need to know that both populations follow the normal distribution. Both of the samples are simple random samples from their corresponding populations, or else you have a collection of individuals and they get randomly assigned to the two groups, so they're independent of each other. Observations within the sample are independent of each other. The sample size should be small relative to the population, less than 5%, otherwise you need to put in a correction factor. And as I mentioned before, the data points from one sample are not paired with data points in the other sample. We don't have matches. Okay, so here is our step-by-step. As usual, we are going to find the significance level, the alpha. We also are going to make sure that we check assumptions, so I guess this would be like a step 0. So that's assuming that all those assumptions are met. Then we're going to determine our null and alternative hypotheses. So this is very familiar. This is the same sort of thing we've done before. So if we have a two-tailed test, we're going to put half the alpha in each tail. So we'll have alpha over 2 here in the left tail, and we'll have another alpha over 2 in the right tail. And then for the one-tailed tests, all the alpha will be in one of the tails. So it could all be in the left tail, or it could all be in the right tail. If it's in the right tail, then we'll just call them, then mu1 is bigger than mu2. For the left tail, mu1 is smaller than mu2. You're going to have to be careful that you keep the mu1 and the mu2 in the same order throughout your problem. Okay? So, as before, our one-tailed tests are assuming that the other direction is not possible. We'll put a star on that one, or is of zero interest. You have to have a rationale if you're going to do a one-tailed test. Then we're going to sketch our rejection region. We need to both compute the test statistic and find the critical value. It doesn't matter what order you do those in. Let's look at the critical value piece first. The critical value of t, what we're going to do is we're going to use our t-table, and we're going to use the degrees of freedom for the smaller of the two sample sizes. For our test statistic, what I want you to notice here is, remember when we talked about the hypothesis test. Let me scroll back to those. So we're going to be set up with our hypotheses. Our null hypothesis is going to be mu1 equals mu2. But keep in mind, that's the same as mu1 minus mu2 equaling 0. So basically what we're going to do when we do our test statistic, we are going to assume that mu1 minus mu2 is equal to 0. So we are going, basically my benchmark for this is 0. Not for the population means, but for this difference. So I am going to replace this with 0. Okay, so that second bit turns out to be 0. So then, once we replace that with 0, what do we get? We get x bar 1 minus x bar 2 divided by this approximation for our standard error, S1 squared over N1. Remember, S1 is your sample standard deviation for your first sample. S2 squared over N2. So, what does this turn out to be? Subtract what you're comparing, right? And divide by the standard error. If you think I've said that a few times, you're right. And it's because if you can remember that, you're going to be in really good shape on remembering how to do all these hypothesis tests. Because that way, if you remember that, then all these hypothesis tests where our test statistic looks different, they all look basically the same. They all look like subtract what you're comparing, divide by the standard error. And then you realize they're just different versions of exactly the same formula. Okay, and so then, as usual, we take our calculated value of our test statistic, we compare it to our critical value, we look on the picture to see if it's in the rejection region or not, and then we decide whether we are going to reject the null hypothesis. Let's do an example. Actually, before we do an example, let me mention what the confidence interval looks like. We're going to start with the hypothesis test, but as usual, there is a related confidence interval that goes with it, and this confidence interval is going to be for the difference between two means. So here, once again, I'm focusing on what these confidence intervals have in common with all the other confidence intervals we have done, so that if you wrap your brain around that, you'll see all the confidence intervals for all these different situations are essentially the same. So basically, what do we end up with? For my confidence interval, we end up with our point estimate for whatever we're trying to approximate, minus my critical value, which is basically a multiplier that tells us how many standard errors away from the mean we are. We're going to have that multiplied by the standard error. So we're treating that critical value, that z or t, as a multiplier that tells us basically how many standard errors we're going to subtract or add from our point estimate. So our point estimate plus or minus my critical value times my standard error. Okay? And so that's our general approach to the confidence intervals. And if you look at these really messy, scary looking formulas, you'll kind of see what that is. So that x bar 1 minus x bar 2, that's the point estimate for the difference between the two means. So we don't know the difference between the population means, so what's the closest we can get? We can subtract the sample mean. So there's our point estimate, and then plus or minus our t. Remember, confidence intervals are always two-tailed, so that's why the alpha is being cut in half. And then what's in this last bit? That's my standard error. And so that standard error is the same standard error that goes into your test statistic when you do the hypothesis test. Okay. Now let's do our example. So you may want to pause and read this paragraph yourself before you listen to me talk through it. So let's say that an inventor has come up with a new produce container which they think will extend the life of fruit in the refrigerator. The inventor buys 3 dozen apples and randomly chooses 12 of them to put in the new containers. Apparently we only have 12 containers. And then the other 24 apples go into the standard bags. And then the containers and the bags will go into the fridge. And then for each apple, our researcher, our inventor, recorded how long it took for the apple to develop visible mold. Okay, and then we took an average for the ones in the containers and a standard deviation, and then did the same for the apples that are in the bags. And all those results are given here. And then we want to perform a hypothesis test to evaluate whether the new containers help the apples last longer. And we're going to use alpha equals 0.05. And we're also going to construct the confidence interval for the difference between the means. We have an assumption here that we can assume that the time for the mold to grow is normally distributed. Okay, so let's look at this. So our sample information okay, so what all do we have? You're going to have more here than you're used to having because we've got 2 samples. So we should write down which one is which. Sample 1 and sample 2. So we should describe these in words. So one of these is containers, and the other is bags. So here's our sample information. Containers and bags. Okay, so for how many of them are in a container? We'll call that N1. How many containers? We have 12. How many bags? 24. So then we're going to work through all this. For the apples in the new containers, the mean time to develop mold was 6.5 days. So that's x bar 1 equals 6.5. And the standard deviation, so that's S1, is 0.9 days. Okay, and then for sample 2, x bar 2, these are the bags. The mean time to develop the mold was 5.2 days. And then the standard deviation was 1.2. Okay, so there is our sample information. Okay, we're going to need the degrees of freedom for each of these, so we might as well do that here. I'm just going to treat df as a variable and call it df subscript 1. So this is going to be subtract 1, 12 minus 1, so this gives me 11. And then my df2, that gives me 24 minus 1, so 23. Okay, so that's our sample information. Let's write our hypotheses. Okay, so my H0 is, so I'm going to assume that my two populations are the population of all apples stored in containers versus all apples stored in bags. And so this would be mu1 equals mu2. So we're going to always have equality for that one. And then now for H1, what we need to do is we need to decide if we're being steered in a direction. Do we have a one-tailed test or a two-tailed test? So we come up here to our problem and we look for the place where it's asking us what we want to find and talking about the test we're going to do. Perform a hypothesis test to evaluate whether the new containers help the apples last longer. So, is this steering us in a direction? Yeah, it seems to be implying that if anything, it's going to make them last longer. And it may be, I don't know anything about apples, but it may be perfectly reasonable that the new container won't make them last less time, but it could possibly make them last longer or else be the same. So this is a one-tailed test, right? So this tells me that we have a one-tailed test. So then, now here you have to be careful about your direction. So that's why we need to make sure we know which one is the containers and which ones are the bags. So the containers, you want to see if that mean time to mold is longer. So it's going to be mu1 bigger than mu2. And so then what is my alpha? 0.05. So we take that 95% confidence level, subtract from 1, or actually it looks like the alpha was just given to us. Okay, so we get that. Okay, so now what do we do next? We need to draw our sketch and then figure out our critical values. So let's do our sketch. Okay, so here we want to think, okay, we have a one-tailed test, so that means all the alpha is going into one side. So here is my alpha equals 0.05. And then this is basically going to be the distribution of the difference between the two means. And I'm going to make a little note here because we have to be careful about which one comes first. So notice I'm keeping x bar 1 in front consistently. You could do it the other way around also, but in order for the mu1, we're assuming that if anything, the x bar 1 is bigger, right? And so that means that that shaded area is going to be on the right side rather than the left. So now we want to write down our critical value. Well, we're going to first write down the variable for our critical value. This is going to be t 0.05. We haven't figured out what that is yet. Okay, so that's our general layout of our picture. So now what we need to do is we need to find our critical value. Okay, and this is our t. So remember when we were doing a one sample hypothesis test of the sample mean against a benchmark. If we did not know or have an estimate for the population standard deviation up front, which is usually the case, then we have to use the sample standard deviation as an estimate, and it turns out that that puts us into the student's t distribution instead of the z distribution. And so the same thing is basically happening here. We're using the t's, not the z's. So what we're going to do for that is we want to use the smaller of the 2 degrees of freedom. So if we look back at our sample information, which I think is still showing here, we have that DF1 is going to be 12 minus 1, or 11, and that DF2 is equal to 24 minus 1, or 23, and so we are going to use the smaller of these, and so that means the 11, right? So we're going to use the smaller of those two. And so then we are going to go to our t-table. And we're going to use a degrees of freedom equals 11 and a right tail area of 0.05. Okay, so let's go to my t-table. Okay, so degrees of freedom equals 11, right tail area of 0.05. Look where those cross, we end up with what? 1.796. Okay, so I'm going to put that on my picture. So now, what if this would have been a left tail test? So this one happened to be a right tail test, but just sort of keep in mind, I know the t-table is set up to do the right tail area, but what if this all would have been negative, and then this shaded area would have been on the other side? So remember, the t-curve is symmetric, right? So if you would have been looking for something on the left side, you would just go look up the positive version of it, and then you would put a negative sign in front of it, and then you'd be good to go. Okay, so now what we need to do, we're almost there. So now what we need to do is we need to calculate the test statistic. Okay, so to calculate the test statistic, the first thing I'm going to do is figure out my standard error. Okay, so my standard error, this is going to be an approximation for the standard deviation of the sampling distribution of the difference between the two sample means for all possible samples. Whew. Okay, so I'm just going to call it that for shorthand because I know that stands for my standard error. I'm going to think of it in my brain as just standard error. I'm not thinking in terms of those symbols. I'm just using that as a label. If you want to just label it standard error equals, I think that is great. Okay, so here my standard error is equal to S1 squared over N1 plus S2 squared over N2. Add those together and divide by, add those together and then take the square root of the result. Okay, let's put our values in. So here we go. I'm going to scroll back to where I had the sample information. So what are my standard deviations? 0.9 and 1.2, and what are my sample sizes? Oh, sorry, don't look at the degrees of freedom, look at the sample sizes. The 12 and the 24. So this is going to be 0.9 squared over 12 plus 1.2 squared over 24. Okay. And I'm going to write down the result that I get, but then I'm going to explain how I get it in my calculator. So I ended up with 0.35707. Now, if you're not sure how to put this in your calculator, so basically in my calculator, here's what I'm going to do. I don't do that square root until afterward, because then you have to keep track of parentheses, and it's really hard to look at, and it becomes very confusing. So I always try to do the most complicated thing first, and then I have to divide by something or raise it to the square root. I do that at the end. So here's how I would do it in my calculator. I would do 0.9 squared. So you could use your squared key, or you could use your raised to a power key, and then divided by 12 using your slash key or your division key. And so 1.2 squared divided by 24. Remember, your calculator knows the order of operations, so it should know to square those numerators before it does the division, and then to do the division before it does the addition. If you don't have a calculator that knows the order of operations, well, you need to get one. So, but they pretty much all do. Okay, and then I'm going to hit enter. So once I have all that. So notice I don't really need parentheses around those numerators. It's better to write it with parentheses like in the formula above, because otherwise with a decimal it can become a little bit confusing. It's more clear to have the parentheses, but your calculator does not need the parentheses. Then what you're going to do is you're going to do square root of your answer. So you use whatever your square root key is, however you do that, of your previous answer, however your calculator lets you pull up the previous answer. Or the alternative for that is you could raise the result that you got from the previous step to the 0.5 power. That's what I usually do because it's fewer keystrokes. So as long as you feel comfortable with a fractional exponent, that exponent of 0.5 is the same as taking the square root. Either of those methods will work. That's how I would put it in my calculator. I suggest doing it for this example in your calculator. Make sure you can duplicate this result that I've got. Okay, so I got 0.35707. I am going to store this in my calculator in a variable, like for example variable A, so that I can retrieve it later. Okay, so now we haven't calculated test statistic, but now we've got the standard error. Okay, so now we do our test statistic. So for my test statistic, so once you've got the standard error, then the test statistic is pretty easy. And that is going to be T equals, okay, so how's the general layout for a test statistics? Always. We are going to subtract what we are comparing, and then we are going to divide by the standard error, right? And I have no problem with you just writing standard error into that denominator so that you know what's going to go there. That is totally fine. Okay, so in other words, if you want to write it like this, I'm good with that. Okay, and so then, what are we going to do? Okay, so what are we comparing? We're comparing our sample means, right? So we're comparing the sample mean for one sample against the sample mean for the other. So I'm going to scroll all the way back up here, find my sample means. What do I have? 6.5 and 5.2. Be sure you keep this in the same order you've used all the way along. So what you want to do is you want to label one of the situations as sample 1, the other situation as sample 2. Then when you do your hypotheses, then the mean for 1 ends up on the left, for 2 on the right. When you do your subtractions, you always have sample 1 minus sample 2 in that order. It does not matter. We could have done the bags first and then the containers. That would have been totally fine as long as we did it the same consistently throughout the entire problem. So you want to keep track of which one should come first. So this is going to give us what? 6.5 minus 5.2. divided by this 0.35707. I'm going to use the stored value that I got from my calculator. I'm going to retrieve that variable a wherever I put it, and so this gives me 3.64. All right, we're almost done, I promise. Okay, so now 3.64. So now what do? We need to go back to our picture and we need to put this 3.64 onto my picture. So where's my picture? Positive 3.64. Okay, that's definitely in the rejection region. So that's going to be over here, right? So this is my t equals 3.64. And so now I want to write my conclusion. Okay, so that t equals 3.64 is in my rejection region. And so we are going to reject our H0. Okay, and so then we want to be able to reframe this problem in terms of the actual situation. So you may want to go back and reread your H0 that we just rejected. So what did H0 say? mu1, that's the population, the mean of the population of all apples that are stored in containers, is equal to mu2, which is the mean of the population, the molding time for all the apples stored in bags. So we're rejecting that, which is putting us down. We've got evidence in favor now of the H1, the alternative hypothesis, even though, of course, we haven't proved it. All we've done is rejected H0. But so this does seem to be giving us evidence that the mean time for mold for population 1 is greater than the mean time for mold for population 2. So at least based on this sample, that the apples last longer in our newly invented containers than in bags. Okay, so maybe our inventor can approach somebody about selling these or making prototypes, or at least we have some promise here that this might work. Okay, so that's how we do our hypothesis testing.